osmosis. So first let's have a look at what osmosis is. So osmosis is the movement of water molecules from an area of high water potential to an area of low water potential across a partially permeable membrane. So let's break this definition down. So first, it's the movement of water molecules, specifically water molecules. It's from high to low, meaning it's a passive transport, and passive transport purely means that the only energy needed for this transport is the kinetic energy of the particles moving themselves. No extra external energy is needed for this transport to happen. Then it's about water potential, high to low water potential, and water potential is the pressure created by water molecules. And lastly, it's across a partially permeable membrane, and this is just plasma membranes being selective, and most plasma membranes let water and other small molecules through, and this is why they're just partially permeable. So water potential. Water potential, as I said, is the pressure exerted by water molecules, and this is measured in kilopascals. And water potential is represented by this symbol here. So under standard conditions, which is 25 degrees Celsius and 100 kilopascals, water potential of pure water is 0. So pure water under standard conditions has a water potential of 0. The water potential cannot be more than 0. And this is because as you add solutes, the water potential decreases, it gets more negative, and you cannot get more pure than pure water. And if pure water is 0, you cannot have a water potential more than 0. So now let's have a look at the process of osmosis. So here you can see we have differencing concentrations of our solute, and this is glucose. And this is a partially permeable membrane, and these tiny spheres are water molecules. So both the water molecules and the solute molecules move in random motion, and this is due to their kinetic energy. So all of these are moving around. And even if there are the same number of water molecules on each side, the side of the partially permeable membrane with more solute has more attachments to water molecules. So this does not allow the water molecules to move separately. So the side with more solute has a lower water potential. And let me, for example, show you here. If we had a solute of sodium, the water molecules would attach to this sodium, leaving less water molecules to freely move around, meaning the water potential, the pressure exerted by the water molecules would be lower because there are less water molecules bouncing around, creating pressure. Next, the partially permeable membrane only allows the water molecules through it, not the solute, and this is very important. So this means that the water molecules from the higher water potential diffuse over the partially permeable membrane into the lower water potential, because in the higher water potential there are more frequent collisions between the water molecules, causing them to be propelled towards the membrane, crossing over into the lower water potential. So when the water potentials are equal on each side of the partially permeable membrane, they reach a dynamic equilibrium, so there's no more net movement of water. And this simply means the water molecules still do move across the partially permeable membrane, but there's no overall movement. So there's not more movement of one side to the other. There's equal amounts of water being in and out. It's reached a dynamic equilibrium. So now the situations of water potential. There are three possible situations, as you can see here. The first, hypotonic. And hypotonic is when there's a higher water potential outside the membrane, as you can see here. So there's more water molecules outside of the membrane than inside. Then there's hypertonic. And this is when there's a higher water potential inside the membrane. As you can see here, there are more water molecules inside of the membrane than outside of the membrane. And then there's isotonic. There's equal water potentials either side of the membrane. So the pressure exerted by the water molecules inside the membrane and outside the membrane are equal. And let's put this into practice. Water potential in plant cells. So here's our table. So when the water potential is hypertonic, so there's higher water potential outside of the plant cell, this means that the net movement of water is into the membrane because there's a higher water potential outside, lower inside, so it moves into the membrane. And this means that the plant cell becomes turgid, swollen, because the water molecules have moved into the cell. Now, hypertonic, a higher water potential inside the cell, meaning that the net movement is out of the membrane because osmosis works from water molecules moving from higher to lower water potential, meaning if it's higher inside the cell, they'll move out of the cell. And this leads to the plant cell becoming plasmalized. As you can see here, as the water molecules move out, the plant cell is left plasmalized. And lastly, isotonic, with the same water potential inside and out of the cell, means there's no net movement of water. So the plant cell remains flaccid. And this just means it's loose. As you can see here, same water molecules moving in and out. There's no net movement of water molecules. And now, water potential in red blood cells. So here's our table again. Hypertonic, when there's a higher water potential outside of the cell, means there's a net movement into the membrane. And this leads to the red blood cell undergoing hemolysis, meaning it swells and bursts. As you can see here, if the water moves into the red blood cell and it's a net movement into it, it will swell and burst in hemolysis. Now, hypertonic, when there's a higher water potential inside of the cell, so there's a net movement out of the membrane, the red blood cell undergoes crenation, where it shrinks and collapses because all the water gets taken out of it. And lastly, isotonic, when the water potential is the same inside and out of the cell, and there's no net movement of water molecules. The red blood cell will remain unchanged. It's in equilibrium.